Our committee has several working groups. We've been at work for 2 years, and in that time we have amassed quite a lot of knowledge, both about the nature of solid-state light and the story of how we got to this juncture. We've not confined the study to LEDs. We look at all SSL sources. We've presented a SMPTE paper, created some very powerful computer tools to assist us in studying the issue, shot a lot of photographic tests in the lab, as well as simulated production footage. We visited the National Institute of Standards and Technology, NIST, and embarked there on what we look forward to being a very productive relationship. We've built an expanding database of literature and patents, and of course, established a website where much of this is available. Last May, we produced a public program with a demonstration on film shot by Darren Okada called The Experiment, and we'll share some of that with you today. That program also contained a tutorial on the science of color. It's available on the website. Here's a segment from the film Experiment which illustrates some of the problems we've observed.
We chose the red velvet chair with the tufting, the Victorian style, because we all love the interaction of the play of the folds and the shadows, and of course what Michael was talking about the fibrous nature of the material and how it catches light. Number two is starting to impact that quite dramatically. It almost might say, oh good, look, we got a free aging job.
It's necessary to understand what produced the artifacts seen in the experiment footage. To do that, we need a summary review of LED technology, as well as a little explanation of spectral power distribution and color rendering. The current commercially obtainable white LEDs are constructed along much the same lines as the fluorescent tube. Instead of a short-wave ultraviolet excitation emission and a recipe of phosphors, the LED uses a blue emitter with an emission at around 450 nanometers to excite a phosphor that, with some variations, is producing a sort of orange light. The designer hopes that the integration of blue and orange will be the equivalent of combining red, green, and blue and producing white. And superficially, this is demonstrably the case. In the demonstration film Experiment, our panelists were uniformly confounded by the fact that their on-stage observations were that the light looked uniformly white, while the screened reproduction showed it clearly was not. This shows a comparison of the standard studio tungsten light to one of the LED white lights used in our test. The discontinuity is quite obvious. Even though the light appears to be white, it is incapable of recording many subtle shifts in hue and saturation that the real colors of the world present to us and that we as filmmakers are under an obligation to deliver to our audience. That said, human technological genius is demonstrably sufficient to solve the problem and produce a close approximation to the smooth, continuous emission that has characterized essentially all of our predecessor light sources such as candles, oil lamps, gas lights, and incandescents. However, as things stand, there is no such requirement in the proposed legislation either here or elsewhere in the world that will ban many incandescents by 2014. Here is what Crandell et al. Had to say in their 1949 SMPE paper on the issue of discontinuity. What we are interested in is a continuous spectrum, which will be recorded on film, and it's desirable that the general curve of spectral energy distribution be reasonably smooth, so that it will not show any unpleasant surprises in connection with colors having narrow absorption or reflectance bands. Later in this session, we'll discuss the lighting industry's use of inaccurate and irrelevant indices such as correlated color temperature, CCT, and color rendering index, CRI, to describe their product's color rendering. But just now, let's look at the effect of the discontinuous nature of LED illumination on the spectral response curves for imaging devices, our cameras. As we've discussed, film and digital cameras are designed to produce a specific color rendering of our world. To do this, the film or camera designer creates spectral response curves. The film will record colors according to the degree of its sensitivity across the spectrum. To achieve his goal, the designer had first to establish what would be the baseline quanta of energy across the whole spectra illuminating the scene. And as we know from Mr. Hankins, since 1951, all professional color film used in the motion picture studios has been balanced for exposure with tungsten illumination. The salient point then is, if you change the illuminant from the design illuminant to some other, then you have overridden the film stock design color rendering. It's that simple. Here we can see how that occurs. And yet, such sources may fairly lay claim to seductively attractive CCT and CRI values, to the very expensive dismay of the unwary cinematographer. So there's an immediate and quite critical need to provide a more effective index, or rather indices, to assist the cinematographer in selecting these new instruments. The International Commission on Illumination, the CIE, in the 4th edition of the International Lighting Vocabulary, defines color rendering as the effect of an illuminant on the color appearance of objects by conscious or subconscious comparison with their color appearance under a reference illuminant. The color rendering index, then, is a numeric scale of from 0 to 100, with 100 indicating a perfect match between a sample light, which may, for example, be a fluorescent or an LED, and a standard reference light, such as tungsten at 2950K. Correlated color temperature, CCT, designates the approximation of the color temperature of a sample light, such as fluorescent, to a black body, such as tungsten. Neither the CRI nor the CCT have any relevance to color rendering in photography. The formal definition of the CCT by the International Commission on Illumination is the CCT is the temperature of the Planckian radiator whose perceived color most closely resembles that of a given stimulus at the same brightness and under specified viewing conditions. The irrelevance of the CRI, or for that matter any existing color rendering index in color photography, is based on the fact that such indices are intended to gauge how accurately a color is matched using various illuminations of a set of standard color chips as observed by the human eye and compared to a standard reference illuminant. There are thus three elements: the human observer, the color chip, and the light. Two, the human observer and the color chip, are invariable, while one, the light, is variable. Various manipulations of a sample light can lead to some degree of a color match to which a numeric CRI value may be attached. However, color reproduction in motion pictures involves a fourth element, the unique color rendering of the cinema system, comprised of film or digital camera sensors, the intermediate process, and the display device, yielding the image displayed to the eventual human observer. This fourth element effectively comprises a filter through which the world is viewed by the audience. This filter is unique, and indeed it's intended to be so. It's intended by its designers to yield not necessarily an exact match to real-world colors, which it couldn't in any case, but rather a particular interpretation, the verisimilitude of the world, one that, within the context of the motion picture display system, conjures our world rather than reproduces it. After all, the contrast ratio and sheer luminance of light available for viewing motion pictures is a mere fraction of that prevailing in the real world. Our eyes have literally to operate in a different gear. So creating such an illusion of reality is a technological tour de force and the very essence of our art. The film stock design, then, is the variable, and it should be the only variable, since the interaction of more than one variable at a time can cause a sort of chromatic phasing, resulting in moire-like amplification and/or cancellation effects. For example, the green cast from fluorescent tubes, which is the result of the coincidence of the green mercury emission spike and the peak of the film stock green sensitivity with consequent amplification. The situation is exacerbated if still more variables are introduced in the form of yet more light sources with still more varied spectral power distributions, resulting in what I have come to call chromatic chaos.